that we talked about was writing an equilibrium constant expression where we have products raised to their stoichiometric coefficients over the concentration of the reactants. In terms of this, so the concentration in terms of moles per liter. Then we talked about what happens to K when you reverse a reaction, and we found that the new K that you get for the reverse reaction is 1 over the original K. When you multiply a reaction by a factor, you raise the equilibrium constant to that factor, to the power. So Km, the multiplied reaction, is equal to K sub C raised to whatever factor you've multiplied, N. Same thing applies when you half a reaction. You multiply by 1/2, essentially take the square root of K. And then if you add reactions together, the overall reaction is overall K is going to be equal to K1 times K2. If you have multiple reactions that you're adding together, more than 2, you just keep multiplying by K, however many Ks you have. Questions on that? All right. I was working through putting some more homework up for you guys, and I came across another way of writing K. So we're going to be using K sub C a lot. You'll see just regular K, no subscript, and the homework also uses KEQ. All right, so these are all the same. So when you see that, just expect that it's with the concentrations. All right. So I mentioned last time that typically we're looking at equilibrium constant expressions in terms of molarity, and that's our K sub C. But sometimes we use partial pressures as well for our equilibrium expressions. So for instance, if we had a reaction, general reaction, A plus B in equilibrium with C plus D, and these are all gases, we can write our equilibrium constant expression in terms of K sub C or K sub P, where K sub P is going to be equal to the partial pressure raised to their stoichiometric coefficients, like so. Whoops. Okay. It's important to point out that the partial pressure of a gas is proportional to the concentration based on PV equals nRT. Okay, so if we divide both sides by V, we'll have our pressure for a particular gas, and I'm going to write this like this, is equal to N over V times R times T. And N over V is moles over volume. We can say liters. And therefore, P is proportional to moles per liter. Okay? And that shows up in this expression, where we can convert between K sub C and K sub P. So K sub P is equal to K sub C times, in parentheses, R times T raised to delta N. And in this case, R is 0.08206 liters times atmospheres over moles Kelvin. Delta N, if we go back to our generic expression, is equal to the stoichiometric coefficients of the products minus the stoichiometric coefficients of the reactants summed together. So it would be C plus D minus A plus B. Okay, so you sum up the stoichiometric coefficients in the products, subtract the sum of the reactants. And there could be more than There could be one reactant or product, or two, and the rare occasion 3. So let's work this problem. So we have at 573 Kelvin, the equilibrium constant K sub C for the hot air process is 9.60. What is Kp at this temperature? Again, you're given R. The tricky thing here is determining what delta N is. And it's important to note that the stoichiometric coefficients that go into delta N, this is only gases. We're going to see later on that we may have reactions that are in different phases, have components in different phases, heterogeneous reactions. So in this case, it's only the gases that are going to matter. All right. So just kind of working through this, K sub P is going to be equal to K sub C, which is 9.60, times R, 0.08206 liters times atmospheres times mole Kelvin. We need to have our temperature in Kelvin, and that's what's given, 573 Kelvin, raised to delta N. What's delta N for our reaction here? -2? Everyone agree? Cool. All right, that's what I get. And again, we talked about being messy with units on K sub C because we can end up with some wonky looking moles per liter squared or cubed or whatever. Again, we don't need to worry so much about the units on K sub P. It's going to be a unitless number. And I end up with K sub P is equal to 0.00433. Make sense? Questions on this? Okay. Questions on that? This is really exciting, right? So a lot of equilibrium is just going to be some algebra. And that's really what the next remainder of the chapter is going to be. So we're going to have you on this. This is 19. So we have our hot air reaction. So we have nitrogen plus 3 hydrogen in equilibrium with 2 ammonia. Everything's in the gas phase. We've written out the equilibrium constant expression. So K sub C is equal to NH3 squared over N2 times H2 cubed. And we know, we've taken a sample, and we know that at equilibrium, the concentration of N2 is 1 molar, the concentration of H2 is 1 molar. I want to know what is NH3. And in order to solve that problem, you need to know what K is, and it's 4.1 times 10 to the 8 at whatever this temperature is. So this is a large value of K. So would you expect to have more reactants or products at equilibrium? Products. All right, so let's do the calculation. I'll have you guys work on that. Feel free to talk with your neighbor. We'll see what number we come up with. I think we did something like this Wednesday, right? Any questions? Questions? Concerns? Any questions? Is it going back here? Only you today?
I think so. I know that there's a thermo exam, so.
Oh, yeah. Exam week for everyone, right? How are you doing? Yeah? How are exams for you? That's good. Good.
Did you get the presentation sheets?
Yes, I did. Thank you. Welcome. It's okay. Any questions back here? Questions, concerns? Anyone have any questions? All right. All right, so hopefully you've worked through a little bit. You end up with, if you're rearranging your equation, you end up with NH3 is equal to the square root of K sub C times N2 times H2 cubed. We know that our Kc is 4.1 times 10 to the 8th. N2 is 1 molar. H2 is 1 molar. So, and that's cubed. And so we end up with the basically just the square root of 4.1 times 10 to the 8th. And I end up with 2.0 times 10 to the 4th. And here we can include molar. So let's compare this value, 2.0 times 10 to the 4th, to what we found for N2 and H2 at equilibrium. It's huge, right? So we predicted that we would have a product-favored reaction at equilibrium because our K value was very large. We go back and look, compare what we have for NH3 for our product compared to our reactants. at equilibrium, that holds true. Okay? Questions on problems like this? All right. Yes?
So the solution, like when it comes to calculating the equilibrium of the solution, would that just be considered like the three gases that are present?
Yeah, so in the total volume?
Yeah, like just thinking about what all is present.
So I would say that imagine that this reaction is all taking place in a flask of some constant volume, 1 liter for instance. And so the concentrations are going to be changing until we reach equilibrium, but the volume won't be changing. I don't think I answered your question.
I kind of get it. Like, I just wondered, like, what all is assumed to be present? Like, it's just those three gases?
Yes, it is just those three. Yeah. So you could think about maybe, and maybe a better question would explain what was happening a little bit more. So let's say we put some amount of N2 and some amount of H2 in a flask, sealed it off, allowed it to come to equilibrium, and we get this. Cool. Okay, so here's another one. I'll have you all work this one as well. So we have nitrogen plus oxygen in equilibrium with nitrogen monoxide, all gases. The K value here is 4.6 times 10 to the minus 31. So this is very small. At equilibrium, again, we'll say we allow this reaction to take place in a flask, sealed flask, and we find that at equilibrium we have a concentration of N2 of 1 molar, a concentration of O2 of 1 molar, and we want to know what is the concentration of NO at equilibrium. So NO is the product. You're looking for would you expect a small value or a large value in comparison to 1? Small, okay. So when I'm working these problems, I like to work these out pretty stepwise, kind of stick to a plan. First thing I like to do is write out the equilibrium constant expression, so I recommend doing that as well. So that's just products over reactants. You can include the value for K if you're given one. And then rearrange in this problem and solve for NO. So again, give it a whirl. Feel free to talk to your neighbors. All right. So this problem ends up being very similar mathematically to the previous one we just did. So for K sub C, I have NO squared over N2 times O2. When you rearrange and solve for this, end up with the concentration of NO is equal to the square root of K sub C times N2 times O2. And when you substitute in your K value and your concentrations of N2 and O2 and take the square root, you should get 6.8 times 10 to the minus 16 molar. So tiny. Questions on that? Okay. So those last two problems were on the easier side. You basically have one unknown that you're solving for, but that's not always going to be the case. So many times we're going to be given starting concentrations, say, of reactants, and need to find the equilibrium concentrations of both reactants and products. In that case, what we use are ICE tables. We call ICE tables. What ICE stands for is initial, change, and equilibrium. So, and when you use an ICE table, it's really important to put concentration in your ICE table. I know that not every 1210 instructor teaches Bca tables before, change, after. This is when you're like working on maybe acid-base reactions or things like that. But this is very similar. One of the main differences we're using concentration here. So one thing that I like to do when I'm working with these ICE tables is write out the equilibrium expression first, the reaction first. So we'll have, in this case, we're going to look at carbon monoxide plus hydrogen in equilibrium with methane and water. And it's good to include the phases too, because sometimes, as we'll see, the phase will signify that you don't need to worry about that reactant or product. If this were water in the liquid phase, we actually don't need to worry about its concentration. We'll get to that in a little bit, but so it is good to keep your phases listed. So I is going to stand for initial concentrations. Okay, and so what we'll see is we're usually given, I shouldn't say usually, we're often given initial concentrations of reactants and want to figure out equilibrium concentrations of everything. But sometimes you start with products as the reaction is written. So it is possible to start with methane, for instance, and see where we end up in terms of the equilibrium. So you're going to have some values written in the initial concentrations. For the change line, you're going to have very little information, essentially. We're going to use values of x to represent the amount of change that's going to take place during the equilibrium, during the reaction. If the reaction is proceeding in the forward direction, so reactants are forming products, you'll have minus x for CO, and the stoichiometric coefficients matter in this line. So you would have minus 3x for H2. Okay? Because we're going from reactants to products, we will be forming products. So we will be adding some amount x of products. And again, the stoichiometric coefficients drop down here. And then the equilibrium line is simply you take your initial line and you do the either addition or subtraction with the change line, and that's what will go in these boxes down here. Okay? So that's sort of very general what we're going to be doing with these ice tables. Let's actually take a look at one. So we're going to take 1 mole of CO and 3 moles of H2, place those in a 1 liter vessel. They're going to react and come to equilibrium. And then what goes on to say is that at equilibrium, we know that the water concentration is 0.387 molar. Okay? And we need to find the other concentrations at equilibrium. I think we need a K value. Oh, nope, we're good. Okay. So let's just start. So again, use concentrations in the ice table. So we have 1 mole in a 1 liter vessel for our CO. So that is 1 mole per liter for our initial concentration. For hydrogen, it's 3 moles in a 1 liter vessel, so it's 3 moles per liter. We are not starting with any products, so there's no methane, there's no water in the gas phase. I just put a line. In terms of the change, because we only have reactants to start with, we know that we are going to form some products, which means some of the reactants are going to go away. So that's a negative sign. Drop down the stoichiometry, so minus x for CO, minus 3x for hydrogen. That amount x is going to go on stoichiometrically and form methane and water. Okay. Sometimes nice to draw the line so you know what's happening. So at equilibrium for CO, we have 1 minus x for the concentration. For hydrogen, we have 3 minus 3x. For methane, we have x. And for water, we also have x. Yes?
What way can we not use ice table? Is it when you have a solid as your reaction?
I think I missed the second half. So you said at what point can we no longer use an ice?
Yeah, we no longer can use the ice table. Like the mice table, like what's the difference? Is it
Are you saying mice?
Yeah, like with the moles.
Okay. Okay, yes, so that's a different term that I probably haven't heard before, but that's, I like it, that's cool. So our textbook calls those Bca tables. And we will be combining and doing a reaction with the acid base where you do mice table or Bca table and then figure out what moles have reacted, how many moles have reacted, and then go on and do an equilibrium after that. So this is when you have an equilibrium reaction. So the real signifier are these double arrows. If this were an arrow going all the way to the product side, we would know that it completely reacts. We wouldn't need to do an equilibrium table. We could do the Bca table. Cool, good question. And if you had Dr. Clark, he didn't do any of that. I think he just did proportions. Maybe Dr. Kroner too. Okay. All right, so we were given a nice hint in our problem here that said that at equilibrium, H2O is equal to 0.387. And we know from our equilibrium line that H2O is equal to X. So we can say X is equal to 0.387 molar. And given that, we can go on and solve for the equilibrium concentrations of every other thing. So the concentration of CO at equilibrium is going to be 1 minus X. So it's 1 minus 0.387. Uh-oh. Okay, so it's 0.613. Check my math on this one, because I used a different value on my notes. So concentration of H2 is equal to 3.0 minus 3x. So it's 3.0 minus 3 times 0.387. So that should be 1.839. That makes sense, right? Yep. And then CH4 is going to be equal to just X, 0.387. Okay. Does everyone see how we did that? Questions? Yes?
How would we do it if we weren't given concentration of water?
If you weren't given the concentration of water, you would have to know the value of K in order to solve for these things. Sometimes these problems can get a little ugly with your exponents, so in some cases you have to use the quadratic formula to solve it. That's not always the case. Sometimes we can make assumptions about the size of X in relation to starting materials and ignore a small value of X. We'll get to that in a little bit. But there are definitely mathematical ways to do it. Yeah. But you would need to know that, you would need to know K in order to do that with this problem. We can now solve for K. So K is going to be equal to the concentration of CH4, 0.387, times the concentration of H2O, 0.387, divided by the concentration of CO, 0.613, times the concentration of H2, 1.839, cubed. Okay? And don't forget about that cubed. All right? Yes? Oh, isn't mine cutting it off? Sorry. The screen size is very different. It throws me off. All right. So I think this is... Let's actually work this one out. check my math, 0.0393 for K. Cool. Other questions on this problem? All right, so here's one for you guys to try. So we've got a reaction. This is our nitrogen monoxide in equilibrium with nitrogen and oxygen. The K value is 2.4 times 10 to the third. We have a 1 liter flask. It's filled with 0.6 moles of NO, so it's 0.6 moles per liter. We only have reactants to start with. We want to figure out what N2 and O2 are at equilibrium. I'll let you guys work on that. Again, feel free to talk with your neighbors. All right. I'm seeing some good progress. I want to point out one thing before we get in over our heads here on some math. You're going to end up with your K value is equal to x squared over 0.6 minus 2x, and that's going to be squared. You got it. This is a perfect square. All right, so before you go through and FOIL out the, do we still say FOIL? And okay, before you FOIL out the denominator and make it into a big, ugly, messy equation, you can. This is a perfect square, so you can take the square root of both sides and make your life much easier and solve for x. All right? If you didn't get to this part, let me know. All right, so filling in the ice table would look something like this. For the reactant, for NO, you're going to have 0.6 minus 2x at equilibrium. For N2 and O2, you're going to have x. When you work through all the math, you'll find that x is equal to 0.297. And so that's going to be the concentration of N2 and O2. And then the concentration of NO is going to be 0.6 minus 2 times 0.297. And I end up with 0.006 molar. So very few reactants left at equilibrium, which makes sense because our K is very large and we expect our reaction to be product favored. Make sense? All right. Questions on this one before I move on? Okay. All right, so I kept alluding to heterogeneous equilibria. So this is when we have reactants and products in more than one phase. So here we have an example of PCl5 in the solid phase, in equilibrium with PCl3 in the liquid phase, and chlorine gas. Most important thing here is that the equilibrium does not depend on pure solids and liquids. Okay? So, if a substance is a solid or a liquid, it doesn't show up in K. So K for the above reaction is simply K equals Cl2. We still use the stoichiometric coefficients. And in this case, it's 1, so it's K equals CL2. Make sense? You're going to get a ton of problems with this in your homework. Just to make sure those are sort of instantaneously can do this, because this is an easy way to make a mistake on an exam or homework where you're including a solid or a liquid when you don't need to be doing so. All right, another example, and we're going to see this one, is 2H2O. We're going to see this in sort of a slightly different way. When water is a liquid, in this case, and this can be in equilibrium with 2H2 gas and O2 gas. In this case, K is going to be equal to H2 squared times O2. Okay, again, ignoring water as it's a liquid. Okay. The reason we can do this is that if we're at equilibrium, the concentration of a liquid or a solid shouldn't change. So that's why we just leave it out of our equilibrium expression. All right. So, oops. Let's think about how we can determine if a reaction is going to go towards the products, or if we have products present, if it's going to go towards the reactants. All right. So K, our equilibrium constant K, allows us to predict the tendency for a reaction to occur. Is the reaction going to happen in the forward direction? If K is greater than 1, it's going to favor the forward direction, favor products. If K is less than 1, it's going to favor the reactants. And our equilibrium constant will also allow us to predict concentrations at equilibrium for various reactants and products, given initial concentrations. And again, that's by using the ice tables, so we've seen a little bit of that up to this point. The thing that we haven't seen yet, that we're going to get to next, is if we have a given set of concentrations for reactants and products, is the reaction at equilibrium. So what we use to determine that is called the reaction quotient. It's given the symbol Q. And we're going to calculate a reaction quotient. We're going to compare that to our equilibrium constant. And we're going to see which way the reaction should proceed. And so that's going to tell us, if we are at equilibrium, if we're not at equilibrium, should more reactants form or more products form? Okay. So the reaction quotient is essentially has the same form as K. So it's calculated in the same way. But the major difference is that the concentrations used in the equation are not necessarily the equilibrium concentrations. So you're given some concentrations. You may be asked, is this reaction at equilibrium? You have to use Q instead of K, even though Q is simply calculated the same way as K is. It's just a way to sort of signify the difference there. There we go. All right, so so these concentrations that we include in here may not necessarily be at equilibrium. If we find when we calculate Q that Q is equal to K, then the reaction is at equilibrium. If Q is less than K, it means that the concentration of products is less than the concentration of reactants then it should be at equilibrium. And so the reaction proceeds towards the product side, goes in the forward direction. But if Q is greater than K, it means the concentration of products is greater than the concentration of reactants that's predicted by K. So the reaction proceeds towards the reactant side. We're going to do a bunch of these examples so you can kind of get a sense of what's happening calculation-wise. I think this is the shortish one. Yeah, okay. So I think there's a typo as well on your slide, so I missed my 2 in front of the ammonia on our Haber reaction. Stick that in there. Okay, so we have our Haber reaction. We have K for whatever temperature this was performed at. K is equal to 6 times 10 to the minus 2. So some point during the reaction, we take a sample and we find that the concentration of N2 is 1 times 10 to the minus 5, H2 is 2 times 10 to the minus 3, and NH3 is 1 times 10 to the minus 3. So is this reaction at equilibrium? First thing we need to do is calculate Q. So Q is going to be equal to the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 cubed. And if we plug in all of our concentrations that we were given, so we'll have 1 times 10 to the minus 3 squared divided by 1 times 10 to the minus 5 times 2 times 10 to the minus 3 cubed. Okay. And I end up with 1.3 times 10 to the 7th. Okay. So now our next step is to compare our value that we just calculated for Q to the value that we are given for K. And we can see here that Q is much greater than K. We'll use that. Which means that there are more products in this current state than there would be predicted to be at equilibrium. So more products present than predicted at equilibrium. So if that's the case, which way should the reaction proceed? So there's more products present than predicted at equilibrium. So we're going to go towards the reactant side, right? So the reaction needs to proceed towards the reactants to reach the equilibrium. All right. Questions on that? I know this is a place that we've only done one example, but I know this can be confusing. Anyone have any questions? How long can I make you wait before I say go? Have a good weekend, everyone.